Good day, everyone that is watching this, wherever place you are watching from and whatever time you are watching from. I say welcome to our YouTube tutorial video organized by CCC SP Futa by the academic unit. So today we'll be taking Physics 102, and let me put a short note that we'll be tailoring this teaching to Futa curriculum using their textbook, some examples. Although we use some knowledge, but basically it's to help you in the journey during this second semester. Now, Physics 102, the first topic you have in that course is electrostatic, electric field potential, electric field intensity, and but we're going to break it into series so that it will be easier. So we'll be starting with electrostatic. That is the beginning now. I'm talking more about charges. So electrostatic is the study of charge, from the word electricity and static. That is, static means at rest. So electrostatic is basically the study of charges at rest. Study of charges at rest. So by now you can do some little assignments by asking yourself who discovered charge, who classified it, the likes of Benjamin Franklin, the likes of Drufe, and so on and so forth. So those are basic knowledge you should have known, or probably you would have known during secondary school, or things you can do yourself. If you have to do that, I hope you know the time would not permit. So let's go to electrostatic, that is the study of charge at rest. Now let's look at let's remind ourselves of some basic things in charge. We have the types of charge, of which the positive and the negative charge, and this will drive us to the theory, electrostatic or theory of charge, which says that like charges they repel, unlike charges they attract. So if you have a positive charge here and a positive charge here, what do? They repel. But when you have a negative charge and a positive charge, they attract. When you have a negative and a negative, they repel. You understand? Repel means they run away from themselves, just like that magnet that we used to play while we are still a little bit younger. So let's go to the properties of charge now. What are the properties? Some of the properties of a charge. Number one is that charge, is a scalar quantity. Yes, a scalar quantity. Charge can be conserved. Conserve means you can store it. That is why we have all these solar systems. When we charge it, put it in a battery, then we can use it later, so it can be charged. Another is it can be quantized. The word quantized means it is expressed in multiples. You can't have half of it. We don't have half of the charge. The unit of charge is coulombs. So one charge or one electron is 1.6 times 10 per minus 19 coulomb. One electron, 1.6 times 10 per minus 19 coulomb. So every charge we have are multiple of these. Either you have 2 of it, either you have 3 of it, either you have 4 of it. You can't have 2.5 of it. You can't have 0.5 of it. You can't have 2.3 of it. So that's the word quantized. Are we there? So now let's move on to what else should we talk about? Now let's go to the different methods, or the methods of charging, of transferring charge. The first one we'll be looking at is charge by friction. This charge by friction is also called by rubbing. When you rub a body against itself, for instance, that trick we do while we're in secondary school. You take your pen, you rub it probably on your palm. By the time you put it on your paper, it attracts it. So that is, you are charging by friction. In this method, you are rubbing two bodies against themselves. Then electron is transferred into another body. For instance, take a look at glass and zinc. Glass plus zinc. If you rub glass with silk, silk. If you rub glass with silk, the silk transfers electron. Electron is a negative charge, so it transfers the electron to the glass transfers electron to the silk. It transfers negative out of it. You know that we have, in a neutral body, you have a combination of positive and negative, which makes it neutral. I have +2, I have -2. It means I'm neutral. You understand? So when you rub a silk to a glass, you understand, or you rub a glass on a silk, the glass transfers this negative to the silk. So it remains what in the glass? It remains positive. So the glass becomes positively charged at the end of the day, while the silk becomes negatively charged. So that's why they use the English that glass rub with silk gives positive. Glass rub with silk gives positive. But in the case of ebonite and ebonite rubbed with 4. This ebonite transfers electron, which is negative. It transfers electron to this ebonite. This 4 transfers electron to this ebonite. 4 transfers electron to this ebonite. Therefore, it becomes positive. This 4 becomes positive, while ebonite becomes negatively charged. So all this method of charging both the ebonite and the 4 is what you call by friction, because you are rubbing. In summary, glass rub with silk, the glass becomes positively because it transfers the electron to the silk. Ebonite rub before, ebonite becomes negative because it accepts electrons from the 4. While the 4 is giving out electron, it would have excess positive charge. Now let's move on to the other way of charging, that is by contact. This is the common method of charging by contact, when you put them together. So what happens is, if we have, let's say, a block that's positively charged, then you have one that is neutral, then you put them together by contact. This one as well becomes positively charged. It transfers the same charge to that neutral body. So this is by contact. I'm just bringing them together. So this one is by rubbing. This one, by contact. Then the last one you have by induction. So induction is when you charge a body by neutrally. When you charge a neutral body by just bringing a charged body near it, it is not touching it. For instance, look at this hand. Let's assume it's neutral. Then this is the charged body, but it is a conductor. Yes, it can accept charge. You understand? Conductors and insulators. So if you don't know that, you study about that as well. Because conductors, they can conduct electricity. Insulators, no, they don't allow electric current to pass through them. So this body that is neutral should be a conductor, while this one should have a charge. So when you bring them together, not touching, so that it won't be contact, this one gains charge from it by induction, just by merely being beside it. So this is how it works, and we'll draw the principle. Let's assume this is a charged body and it is negatively charged. Let's assume this is a conductor on a lamp stand here. So what do? When you bring this near it, closer to it, it provides, they call it a sphere of, it pushes electron around it, and it pushes charges around it, and it redistributes, it rearranges itself. What I'm saying is, saying that you are bringing a charged substance into this air, it disrupts the air around it. So these charges rearrange themselves here. It is neutral because it has a balanced negative and positive charge. So when it is seeing something that disrupts it, then it brings out that positive and negative that is working together to give it a neutral charge. It brings them out. A disturbance is around also. So you have positive and you have negative charge here. So what happens is that the next thing is, this is the process. You bring the charged body near the conductor. This is the conductor, and this is the charged body. Charged body. So when you bring it near it, now the electron, the charges are already distributed in it, positive, negative. So what happens is that you earth the body. Earth the body means you are touching it here and you are bringing it to the ground. So this one is like by contact. Let's call this a wire. It draws this negative current, into the ground. Then what you have is just, sphere of positive charges in this. You make it big, positive charges, Then you remove your head. Then you take away the conductor. When you take away the conductor, so you remove your head before taking away the conductor. If not, if you take away your conductor before removing your head, it's not going to give you what you want. So you remove your head. Then after removing the head, this is the head. Then you take away the conductor. Then this becomes positively charged. Now, in summary, in this, it transfers electron to it. So you're having like opposite charge now. In this, you're having same charge by contact, while in this, you're having opposite charge. Do you understand? So that's charging by friction, by contact, and by induction. Now we've spoken about charges and different types of charges. We have positive, negative charge. We've taken the theories. So now let's go to the gold leaf electroscope. Gold leaf electroscope. So what is a gold leaf electroscope? This basically is a device we use to test and detect charges. We use it to test for charges. We use it to detect charges. So to see if an object is charged or not, and to know, what type of charge is in an object, and go. So let's go. The gold leaf, basically, I want to give you a little bit of an assignment before we proceed, and that's go get the person who discovered the gold leaf electroscope. What's the name of the man who gave us the gold leaf electroscope? Oh, the woman who gave us the gold leaf electroscope. Now the parts of the gold leaf electroscope is basically you have the golden cap or the gold cap. You have the rod. Sorry, you have the metal cap. You have the metal rod. You have the gold leaf. This is the leaf in a glass container. So this is just a simple way of demonstrating or drawing the gold leaf. So pardon me. So just a simple way of demonstrating it. As you have a metal cap where the object you want to test for is placed, then the metal rod that carries the charges to the leaf, and this leaf tells you, what type of charge it is. Now this gold leaf electroscope works on the principle of electrostatic repulsion, and we already spoke about this. Yes, we already spoke about this. Repulsion means repel. So electrostatic repulsion means like pulls repel. So it is working on that principle. If you know the charge of an object, okay, so let's take it a little bit by bit. Now, how does this work? Let's start with no charge on an object, be uncharged object, uncharged body. If you put a body that is not charged here, definitely, this is contact. This is contacting this. There will not be any charge carried into this metal rod since it has no charge. So if you put something that has no charge on my body, it won't transfer any charge to me by contact. Yes or no? So it won't charge, it won't conduct anything to this. And this gold leaf you are seeing here, nothing happens to them because they are not receiving any charge. So for an uncharged body, no change in the leaf, no change in leaf. The leaf stays in the same position. Now, for a charged body, once this body is charged, what happens? If this body is charged, this is what happens. The charge it has goes into this, then it does something to this gold leaf. So the charge is conducted through this rod into this leaf, and this leaf either falls or diverges. It either converges or diverges. So what we are saying is, if a body is charged, so you want to detect charge. If a body is charged, when you put it on the gold leaf electroscope, it is charged. This leaf either diverges, it changes position. That's the word. But if it doesn't change, it means the body has no charge. Now, if the leaf changes position, how do we know what's the nature of the charge? Is it positive charge? Is it negative charge? So that is what we want to do now. We already know how to detect if it is uncharged or if it is charged. Now we want to know what type of charge it is if it is charged. So if it is charged, there are two things. The first one is you have to know the charge of this body you are putting there. Yes, that's it. You have to know the charge on this body. If it is a positive charge, what goes into here? Positive charge, right? And when it gets to this leaf, if it converges, if it closes up, actually you are saying that it's like coming together, right? If it closes up, it means it is unlike charge. It means the charge, if it closes up, it means they are unlike charges. Or if it diverges more, it means they are like charges. Let me come again. Let's assume what you have here is a negative charge. You must know the charge on this gold leaf, rather. Let's assume what you have here is a negative charge. Then you put a body. There was a mix-up the other time. I said you must know the charge on this body. No, this is the body you want to get its charge. So you know the charge on this gold leaf now. You first charge the gold leaf. You might bring a negative body, put it on this to charge the gold leaf. So now the gold leaf is negative. Take that positive, the negative body away. You already know that this gold leaf is what? Is negative now. So it means you must know the charge on your gold leaf. Do you understand? So you can purposely charge it to whatever you want, either positive or negative first. And then you now take this body you want to get its charge. You put it on this gold leaf. You know the gold leaf is negative. This charge goes into here. If it is positive, it diverges. Positive and negative, it diverges. But if it is negative and the negative it is before, sorry, if it is positive, it converges. Do you understand? That is positive and negative, they come together. But if it is negative, it diverges. Negative and negative diverges. Let me come again. If the charge on this is the same with this body, it diverges. If it is different, it converges. So let's assume first thing I did was to charge my gold leaf to positive. So I know the charge on this gold leaf is positive. Do you understand? Then I put this body on it, and this gold leaf spreads out this way. What does spread out mean? It diverges. What did I tell you would make two charge bodies separate? If they are the same thing, because electrostatic repulsion, they repel. So if it diverges, it means what we are putting on it and its charge is the same thing. So we don't know that charge that we are putting on it, but we know the charge of our gold leaf to be positive. So if it diverges, it means it is the same thing. So it means this body is positive. But let's assume when we place it here, it converges. It means it is an opposite of its charge. Converges. Do you understand? So if it converges, if it falls, some English will use the gold leaf falls up. If it falls, we know they are opposite. So if it is positive, this one will be negative, this body will be negative. So what we are saying is, you must know the charge of your gold leaf. You have to know the charge of your leaf. You can do that by opposite charging the gold leaf first. So if it converges or falls off, it is same charge as the body. If it falls off, the body is same charge as your gold leaf. Or if it diverges, if it falls off, the body is opposite charge as your gold leaf. But if it diverges or increases more, if it diverges, the body is same as your gold leaf, same as gold leaf. So what we are saying is, if you put the body on the gold leaf, if the leaves diverges, they have the same charge. And since you know the charge of your gold leaf, you know the charge of the body. But if you put the body on it and it converges, it means they are opposite. So if you know the charge of this, you know that opposite of it is the charge of your body. So that is how the gold leaf. Okay, so now we'll be looking at the force between charges. We've spoken about charge, and definitely we know when you have two bodies, there is a force that used to be between them according to this gravitational law of Newton. So the same thing applies to charge as well. When you have 2-3 charges staying in the same region, which we call field, there is a force that exists between them. Now we'll be going to the Coulomb's law, which states that the force of attraction between two charges, or the force of attraction between two charges, is directly proportional to the product of their charge and inversely proportional to the square of the distance between them. This is just like a replica of Newton's gravitational force. So the force is directly proportional to the product of the two charges, charge 1, charge 2, and inversely proportional to the to their square of the distance between them. Meaning the higher the magnitude of those charges, the higher the force between them, and the farther they are, the lower the force. The lower the distance, or the shorter the distance, the farther, the bigger the force. So if they are very close by, they have a large force of attraction. If they are very far away, they have a small force of attraction. That's proportional. But if they are big forces, if they are big charges, they have big forces. Do you understand? So now, according to law of mass, when you have a proportionality sign, you have to introduce a proportionality constant when you are putting an equal sign to it. So r squared. So this k is gotten from the formula 1/4 pi rho, while PO is called permittivity. So what is permittivity? Permittivity means how easily how a medium permits a force to pass through it. The way you would run in water will be different from the way you run in air, the way you run in grease and coke. So it is just a measure of how much a force is permitted to go through a medium. Do you understand? So, and the permittivity of vacuum is 8.85 times 10⁻⁻12. So I think that should be farad per meter. If I'm not wrong, the unit. So 8.85 times 10⁻⁻12. So if you impute it in this, your K would give you 9 times 10⁻⁹ Newton per coulomb per meter square, coulomb square. So that is n m raised per minus 2 c raised per minus 2. So this is yes, this is our formula for the force between two charges. So what should we go next? So if you calculate, if the two charges are the same, eventually when you calculate the force, you definitely know that this will be a repulsive force, because two charges repulsive, they repel. But if the two charges are of different sign, then you know, okay, this is an attractive force. So let's do something now. Let's take okay, before I go, let me explain. Now I said this is the permittivity of permittivity in vacuum or free space. That is how force is permitted, the force between charges, how it is permitted to move, how field is permitted to move in air or vacuum. So what if it is in another medium? If it is in another medium, such as air, such as the water. Pause. I said if it is another medium like water, like breeze, any medium you can think of that is not air or vacuum, definitely you can't use this EO, because I said permittivity is how a medium allows force to affect charges in it. You understand? How a medium allows force to affect charges in it. So the way air allows force to affect charges in it is different from how water affects charges in it, how water allows force to act, on charges in it and co. So in that case, you say the permittivity you are using equals to EO times relative permittivity. So relative permittivity times the EO. So they'll give you relative permittivity. Sometimes they call it the dipole moment. Yes. They call it dipole moment. Oh, dielectric constant rather. Sorry, oh. So they call it dielectric constant. Dielectric constant. Yes. So or the relative permittivity. So it means you use this E. And note that by that time you can't use 9 times 10 power 9. So read the question and be careful, while reading. Is it in vacuum? Are you given ER? So if you are using ER, it means you have to first do this. ER times this EO you have. The formula becomes F equals to 1 over 4 pi E, where your E is EO times ER. Then Q1, Q2 over R square. So are we good to go? So this is your force between two charges depending on their product of magnitude and the inverse of their square. So we're going to take a question, but before we take a question, let's take a question, just a random question. Let's assume you have 2 microfarad and minus 3 microfarad microcapacitance, rather microcoulombs in a medium, and the distance between them. So this is Q1, this is Q2, and the distance between these two distance equals to that's your R, 2 times 10 power 3 meter. To calculate the force between them, this in vacuum or air according to the question, or you are not given the medium, so just assume it is air. So you just go 9 times 10 K Q1 Q2 over R square equals to 9 times 10 power 9 times 2 times, this is micro, that's 10 power minus 6, 10 power minus 6. So better view, 9 times 2 times 10 power minus 6 times 3 times 10 power minus 6. You will leave the charges, the negative and the positive, leave it out of it first. That is just to tell you what type of force it would, it's going to be over 2 times 10 power 3 square. So this is your force. So calculate this, 10 power minus 12, so 9 times 10 power 9 times 2 times 6 times 10 power minus 12 over 4 times 10 power 6. So this will be a very small force because the distance is very wide. 9 times 10 power 9, and so you have 54 times 10 power minus 3 over 4 times 10 power 6. Force equals to 3 point times 10 power minus 9, 18, 4, 1, 14, that's 3, 12, 2, so 10.5 times minus 9. You know what type of force this is, because it's between positive and negative, so it's going to be an attractive force. Unlike poles, they attract. Now, the question can go as thus: if the distance, is halved, if the distance is halved, what would the force be? What will the force be? So if the distance is halved, this is the relationship between force and distance. Since other factors are kept constant, only the distance is halved. You know, if you halve the distance, what happens to your force? It is inversely proportional. It means you are multiplying your force by 4. If you halve your distance, that is, let's say F equals to, K, or let me just say, let's use that proportionality constant. Now I'm having my distance. My R is not R again, it is 1/2R. Do you understand? So it becomes 1/4R. So this 4 is coming up. Or let me disrupt, way it looks. This is it. If you halve your distance, if you multiply your distance by 2, R times 2, you are decreasing your F by 4 because it is the square. If you multiply your R by 4, you are decreasing your force by 16 because it is inversely proportional. As this is increasing, this will be decreasing. If it is directly proportional now, as this is increasing, this too will be increasing, but it is inversely proportional. Do you understand? So if our distance is halved, it means half, you are reducing it. So it means your force is increasing, but it will not be increasing by 2 because you are dividing this one by 2. It will be increasing by 4 because it is the square of it. Do you understand? It is the square of it. So a simple way to solve this is just by saying, okay, if I'm reducing my R by 2, it means my F is increasing by 2 squared. That will be F times 4. And what is your F? 13.5. So times 4, that will be 54 by 10 to the minus 9 Newton. If the question had been, if you are multiplying your distance, if you are increasing your distance by 3. So if you are increasing your distance, what happens to your force? You are reducing your force. So if you are increasing your distance by 3, you are reducing your force, but it will not be by 3. It will be by 9 because it is R squared. So I have to divide my force by 9 if I'm increasing my distance by 3. Do you understand? But in the case of charges, if I'm increasing my charge by 2, one of my charge by 2, I'm increasing the force by 2 because it is directly proportional and there is no square or cube or root or anything. So it is direct. So if I increase this by 2, the force is by 2. If I increase this by 2, the force is by 2. If I increase both by 2, that is 2 times 2. I'm increasing my force by 4. Do we all get that? Are you good to go? So go through the video again. Okay, so we're taking another question under electrostatic force. But this time around, you can see we have different forces. We have more than 2 forces. So how do you solve questions like this? There is something we call the superposition theorem. Superposition theorem is basically telling you can add, different forces together. When you if you have 10 bodies, when you get the force between the first and second, first and third, first and this, you can add all those forces together to give you the equivalent force. So that's what we'll be using here. We have 2 microcoulomb, 3 microcoulomb, 4 microcoulomb, and go. But there's something I want you to note before we proceed, that if a force is positive, if a charge rather is positive, for positive charge, force goes with field. Force goes in the direction of field. For a negative charge, force, moves opposite the field. This is what I want you to note because we'll be using that in the calculation. So let's go. The first thing you need to do, we have A, let me name it 1, and 2, B, plus 2 microcoulomb and a negative 3 microcoulomb. So usually, if this is a negative charge, when we go to the next section, we'll talk more about electric field. So electric field, for a positive charge, electric field goes out of it. For a negative charge, electric field enters into it. So electric field is given out by positive charge, but it's taken in by negative charge. So if this is positive and this is negative, so we should note that the field goes this way. Yes or no? It goes in this direction because positive gives out the field, negative takes in the field. So at this point A, which I want to call point 1, we have plus 2u, 2 microcoulomb, and you have minus 3 microcoulomb. So let's get the force between the two, and we've seen you know, the direction of the field. So first F12 equals to K Q1 Q2 over R squared. You know, taking it as in a vacuum of air. K 9 times 10 to the power 9 times the unit of K, let me come again, is Newton meter square per coulomb square. You know, 4 times R square over this 2 C square. That's the unit, not N minus 2 C minus 2. No. So 9 times 10 to the power 9 times Q1, 2 times 10 to the power minus 6, 3 times 10 to the power minus 6 over R square. What's the distance? Let's use 3 meter as the distance. Sorry, the question looks incomplete. So let's use 3 meter as the distance. So we have 3 times 3. So our F12 should be equal to 54 times 10 to the power 9 minus 12. That is minus 3 over 9. And that is 6 times 10 to the power minus 3 Newton. Is it correct? Are we sure? So let's move. Now, let's get the direction of the force. I told you that if it is this is with the field. So let's see if the charge is positive. This charge, it is going this way. This charge is going to meet. Is it positive or negative? It is negative. So for a negative charge, the force moves opposite the field. So it means the force would plan to go this way, but because it is seeing a negative charge here, this is point 1, reference point. Because it is seeing a negative charge here, what happens to the force? The force comes back. So this is the force reaction between point 1 and 2. And according to the standard, when you go rightward, we take that as a positive charge. When you go left, as conventions now, positive is right, negative is left. So because it is going leftward, it's going back to charge 1, we call this a positive force. So our answer here will be, it is a negative force. So we call this minus 6 times 10 to the power minus 3 Newton. This is our F1. Do not stress yourself. I'm coming. So the force goes this way. I said after getting after getting your value, just ask yourself that point 1, point 2, the field is going this way. Why? Because this is a negative charge. So the field enters into a negative charge. It goes out of a positive charge. That's the convention. Positive charge throws out field. The line goes away from it. But for a negative charge, it comes into it. So if we look at where the direction of the field, this is positive, this is negative. So to go this way, I mean this is negative and this is positive. It would have gone this way instead. If this is positive, it would have gone this way. So because it's negative, the field is going this way. And I said if where you are entering into, if where a force is entering into is negative, it will turn back. But if it is positive, it goes down. So where it is entering into is what? Is negative. So what happens to the force? The force turns back. So it goes leftward. So that's the negative force. So value you've gotten, just put negative. Now let's go to between this point B and C. Probably, okay, instead of calling 1, 2, 2, to not disturb you, A, B, gently. Sorry, A, B. Now let's look at BC, the force between BC. That would be K, Q1, or let's draw the field first. This is negative and this is positive for B and C. So where would the field go? You said the field enters into negative, right? The positive throws it out. It enters in. So this is the field. This is the field. Now, this is the field. So let's go. The field goes this way. So to make it simpler before I explain this is point 1, point 2. You are going towards this side. So if the force is seen that, where I'm going to is a negative charge, the force goes back. This is the direction. Now let's leave feed out of it so that it won't get you confused. The force is going this way from point 1 to point 2, from point A to point B. So if the force is that, where I'm entering to is a negative force, is a negative charge, it turns back. So it's turning back. Your left is your is your minus in convention. Your right is positive. So it goes back. So it makes it a negative force. But look at this, from point this to this. It is taking this order A, B, C. So from this to this, the force sees it that where I'm entering into, where you are entering into is what? positive, and according to charge, if you are entering into a positive charge, it goes with that field. It doesn't turn back. It doesn't repel it. You understand? So it means eventually, after getting our answer, this will be the direction of the force, right? So force 1, force 2. So or force AB, force BC. So let's calculate the value for force BC. That would be 3, that is 9 times K Q1 Q2 over R squared. That is 3, 9 times, I don't know what 3 has done for me. 3 times 10 raised by minus 6 times 4 times 10 raised by minus 6. Sorry if you can't see this, over 3 squared because it is in meter. Then we have 9 times 10 raised by 9 times 12 times 10 raised by minus 12 over 9. That cancels 9. We have 12 times 10 raised by minus 3 Newton. So that's just by minus 3 Newton, and this is the direction as we said here. So now let's look at superposition. Says we can add this together. That is force. The force experienced at B is force AB plus force experienced at BC. So that is the force experienced on B. Force AB, that will be negative 6 times 10 to the minus 3 plus the force on BC 12 times 10 to the minus 3. So all you have is 6 times 10 to the power minus 3 Newton. I know the direction because it is positive, it means it is to the right. It is to the right. Are we good to go? So